Okay, good morning to all of you. So let us start today's class. Hope my AV is okay. Okay, thank you, Abhishek. Okay, let us glance at what we have done it in the earlier class. So we have done all these equations, water continuity equation, and we have seen that one variable will be dependent, all other variables are independent, isn't it? So from this statement, so I've explained that choose water discharge in all subintervals except one as independent variable. That means in this water discharges equation, all are independent variables, one will be dependent variables. So that means what? If there are m subintervals are there, so there will be how many independent variables will be there? M minus 1 will be your independent variables, and one variable can be determined from the equation, so which is known as dependent variable. So this we were discussing it in the last class. So that one dependent variable from the discharge rate, Q is your discharge rate, is calculated from this one. This is your dependent variable. As I said, if there are 6 subintervals, then all the subintervals during each subinterval, so the variable will be treated as independent variable, but except one variable out of these 6 variables will be considered as dependent variable. So that one dependent variable will be calculated or determined from using this equation 6. So this is what till this point we have discussed and we have studied the last class, isn't it? So what we have done overall is this hydrothermal scheduling after discretization. So we got an objective function and 3 constraints. So one is power balance equation, isn't it? Power balance equation. The second one is power continuity, and the power generation by hydropower plant equation. So these are the 3 equations we have seen it. So this is your mathematical formulation. So in discrete model, that is after discretization. Okay, now what is the solution? See, always whenever you form a model, you have to obtain the solution. So just getting the model is not the solution. It's a model. But what is the solution of that model? So how to obtain the solution of any optimization problem? There are various solution techniques are available. You might have studied in your mathematics, linear programming problem, big M method. Maybe you might have studied, I don't know whether it is there in your syllabus or not. Even earlier, VTU students had one elective subject on optimization techniques, that is known as operations research. So one elective subject was there. So even electrical students were studying that elective subject. So which is one of the good subject. Actually, in order to say subject, it is a tool. It is a tool used to solve several power system problems or electronics related problems, etc. and all those things. So various techniques are there in order to obtain a solution from the given mathematical optimization problem. So now your optimization problem is, you are saying that minimize the cost, real power generation cost of your thermal plant only, even though it is hydrothermal power plant we are treating. So still we are minimizing the real power generation cost of your thermal plant only, because you know that operating cost of your hydro power plant is almost negligible or zero, isn't it? So and with that one, so we had 3 constraints are there. So that is your optimization model or optimization problem. Now what is the solution for this optimization problem? So you know that one already, we have seen that one. we have taken the Lagrangian method, isn't it? We have seen the Lagrangian method, gradient method, we have seen it. So here, this problem also is solved using non-linear programming technique in conjunction with the gradient method, which is a first order one. Gradient method already you have seen it, isn't it? Dou L to dou X or dou L to dou P, whatever it is. That dou L to dou X is known as your gradient, or dou L to dou Pg or dou L to dou Pl is known as your gradient. So that is your gradient method. So here this problem, this hydrothermal optimization model can be solved using any nonlinear programming technique in conjunction with the first order gradient method. Okay, now how to get this one? Now you know that one. What is the gradient method? So you have to take the partial derivative by applying Lagrangian multiplier L. Lagrangian multiplier L is formulated by augmenting the cost function of equation 1. What is your equation 1? Is a cost function, isn't it? So already you might have taken it, or you might have taken screenshots of this one. So this equation 1 is your cost function. So we have to augment this cost function in addition to your constraints, all the things. So that is Lagrangian multiplier lambda, sorry, L. So with the equality constraints 2, 3, 4, through Lagrangian multipliers or dual variables lambda 1, lambda 2, lambda 3. So earlier we are given lambda 2, lambda 1, lambda 2, lambda 3, etc. without m. Now we are giving this m because it is a discretized model. It is a discretized model. So that means we are divided that one into several subintervals. That means capital M number of subintervals, isn't it? So that's why for each subinterval you have to solve this optimization model. So that's why here we are giving it m here. Understood? So now here equation 2, 3 and 4 are your, equation 2 is your power balance equation. Equation 3 is your water continuity equation. Equation 4 is your real power generation by your hydropower plant PGHM during the mth interval. So we have defined it all these equations, isn't it? So let us, for your convenient purpose, so this is, I will show you. This is your equation 2. You see, this is your function, cost function, equation 1. Equation 1, this is power balance equation 2. Then this power balance, now only I am telling it again, while explaining I will not come back to this slide. You see, this power balance equation has got both the PGH, that is by thermal plant, and PG by hydropower plant. That means real power generation by thermal plant as well as real power generation by hydro plant. So both the terms are there in power balance equation. Please remember this one because I am going to explain it. Again, I will not come back to this equation. This is your equation 2. And then coming back to 3 is your continuity equation, water continuity equation. This is your equation, water continuity equation. Understood? Then coming back to the equation 4 is your real power generation by hydropower plant. So that I have given it. So this we have to augment along with the cost function. Like similarly, how we have done for thermal plant alone. So therefore, Lagrangian L is equal to summation of mth subinterval. You see here, mth subinterval, because it is a discretized optimization problem. So we have to solve it for each subinterval. So let us consider this as a subinterval m. Okay, and this summation of, you see here, see the bracket here. Clear? So this summation holds good for your cost function as well as your constraints. Understood? So that means you are evaluating the cost function augmented with the constraints, 3 constraints, and finally you are adding up all those things during each subinterval. So that's why the summation is for the whole thing. I have represented open bracket, close bracket. So within that one, So what I am going to do, so I am going to represent your cost function of your thermal plant only. Cost function of your thermal plant only. Fine. Next, what we have to do? What we have to do? We have done so many thermal plants optimization problem. Solution, we got it, isn't it? First is, whenever you are applying Lagrangian method, that is Lagrangian multiplier, cost function is augmented with the respective constraints. Now this one minus, so what is that one? Minus lambda 1. There are three constraints are there. So we'll take lambda 1, lambda 2, lambda 3 respectively for each constraints. And m we are indicating it is for mth subinterval. So minus lambda 1 into equation 2. So that means that is the thing you have to represent it. Now you see this is the equation, power balance equation. 2 is your power balance equation which is multiplied with your lambda 1 m. Now again equation 3 is your water continuity equation multiplied with lambda 2 m, multiplied with your lambda 2 m. So therefore, so this is what this one, okay, you are not getting it. Now you see this is lambda 2m of your water continuity equation. Then again plus lambda 3 of your power generation by hydropower plant alone. Power generation by hydropower plant alone. Understood? So that means plus lambda 3 of, so you see this is the equation, total equation. This is your equation 4, which is the equation for your real power generation by hydropower plant. Understood? So this is how you are going to apply the Lagrangian multiplier. So you are going to augment the constraints with the cost function. So because during each subinterval m, so be careful, this summation is for the entire equation. Clear? This is how we have to write it. That's why before writing these constraints, so I shown only the brackets, cost function with the three constraints, 1, 2, 3 constraints we are represented. If you have two constraints, only two constraints, you are going to augment it. If you have only one constraint, you are going to augment only one constraint. And in earlier cases, we have seen that when we are not considered, when you are considered a thermal plant alone, so you had only these two things. You had only these two things. You didn't have water continuity equation and power generation by hydropower plant. Understood? Only these two things. And we have not discretized that one. So with respect to continuity, this one we have done it. So that's why we didn't have m in the earlier discussion. Hope you understood this one. L is equal to Lagrangian is equal to, this is the equation. This is how we have augmented the cost function along with the three constraints. Fine. Now what you have to do? Next we have to apply your conditions, isn't it? So what are those conditions you have to apply? After applying Lagrangian, obviously you have to apply the some conditions. So the dual variables, what are the dual variables here? Lambda 1, lambda 2, lambda 3 during each subinterval. It is lambda 1m, lambda 2m, lambda 3m. These are your dual variables are obtained by equating 0 the partial derivative of the Lagrangian with respect to the dependent variables. You see, you have to take it only with respect to the dependent variable. So you have to take partial derivative of your Lagrangian multiplier and equate it to 0. When you are taking partial derivatives, you have to take partial derivatives with respect to dependent variables alone. These are nothing but your Kuntakar conditions. Same thing in thermal stations also we have seen it. So isn't it? Partial Kuntakar conditions is what? You have taken first order partial derivative with respect to the variables and equate it to 0. Now therefore this equation, in this equation, take the partial derivative dou L2, what are the dependent variables? Is your PGT and PGH. Understood? PGT and PGH. So what are the other variables you are having it? X. So these are your, already I have explained it, which are dependent, which are independent variables, isn't it? So therefore here the dependent variables are your real power generation due to thermal as well as hydro, and your x. X is what? Your storage of water in the reservoir. So it is a dependent variable. Why it is dependent variable? Because it depends on the other parameters, the inflow water into the storage, or it depends on your rain. So that's why it is known as your dependent variable. Clear? Even your thermal generation is also dependent, isn't it? Hydropower generation is also dependent on your storage. So therefore, these are your dependent variables. So take partial derivative of this L with respect to PGT, PGH and XM during each subinterval. M means during each subinterval, that is mth interval we are considering it. Okay. Now let us see here. First, with respect to PGTM, I am taking it. With respect to PGTM, I am taking it. So this equation with respect to PGT, I am taking it. So this is a PGT is there variable. So therefore, what it will become? dc of PGT by dt you will get. And where is PGT? In this one PGT is there. In this PGT is not there. In this one also PGT is not there. So obviously these terms will be 0 when you are taking partial derivative, isn't it? This term, there is no PGT term here, so 0. There is no PGT term in this equation also, it is 0. So PGT term is there here, available here. So therefore, when you take derivative of this one, so it will be lambda 1 m. And PGH is another dependent variable. PD is fixed variable, which is 0. What about PL? What about PL? I told this, I am going to explain. Please keep it in mind, I said. Isn't it? What is PL is equal to for a two plant system? PL is a function of your PGT as well as PGH. I given that one, I explained it, isn't it, in today's class. Please remember this one. This is useful while explaining for the future content. So therefore, here PL is a function of your PGT as well as PGH. Remember that one, PGT as well as PGH. So therefore, PL also you have to take it partial derivative. So dou PL to dou PGT you have to consider. Is it clear? So that's what we have written it here. So this is the equation we are having it. You see this one? Dou L2 dou PGT, real power generation due to thermal plant during mth interval. So cost, first derivative of cost equation minus lambda 1 of PGTM is there. So it is 1 minus with respect to transmission loss is a function of your PGT. So dou PL2 dou PGT. And you are represented M during mth interval. So you are taking partial derivative and equating to 0. This is your conditions or Kuntakar conditions. This is how we applied. First you represent a Lagrangian equation, then Kuntakar condition. That means what are Kuntakar conditions? Take the first order partial derivative with respect to the dependent variables, equate it to 0. Fine. Now what will be the next equation? I am going to take partial derivative dou L2 dou PGH. Dou PGH I am going to consider, or you can consider with respect to XM, anything. So now here you see this is your dou L2 dou PGH is missing here. Okay. This is your PGH. Dou L2 dou PGH. So you are taking partial derivative with respect to PGH. So therefore, when you go back and check your equation where exactly the PGH is available, you see here PGH is available here. So when you take this one, then what about once again PD is constant, PGT we are taking partial derivative only with respect to GH. So this will not come. So with respect to this one, it will be 1 minus, this is a function of your PGT and PGH, similar to PGT I have explained. There is no PGT, PGH term, and here you have PGH term in this equation. So then you have to take partial derivative of this function here. Okay. Now here this is equal to 0. Okay. Then coming back to this one, XM we have to consider dou L2 dou xm you have to consider. So with respect to xm, you can see here, with respect to xm, you are having it xm here. Xm minus m also belongs to xm, isn't it? And in this equation you are having it xm. Here you don't have xm's. Here there is no xm cost function. Here also there is no xm. So here we are not going to get xm. Only in this equation and in this equation we are going to get xm. Okay. So that one we are writing it when you take partial derivative. So the resultant will be this equation, equation 10. Take partial derivative of that one with respect to xm, where m is not equal to m, where m is not equal to m, and also not equal to 0, isn't it? M is not equal to m also equal to 0 because it is subintervals. If you are having 7 days, 0 to 7. So 0 you are not, 0 is not your subinterval. 0 to 1 is your subinterval, isn't it? Similarly, 7 is not your subinterval. 6 to 7 is your subinterval. So that's why the last one and initial one, it is not equal to 0. So those limits we should not consider when we are evaluating the partial derivative of that equation. Clear? So just to take partial derivatives from that equation. These are nothing but your Kuntakar conditions 8, 9, 10. This is the same procedure we have done it for thermal generation alone. Okay. Now substituting equation 3 in 6. So this is for your represent. What is equation 3 is your water continuity equation. What is your equation 6? Just now we got that equation, this equation. What is this Q1? Is your dependent variable. Just now I said over a week 0 to 1 is first subinterval, 1 to 2 is second, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. These are the subintervals. Out of these subintervals, all are independent variables. Water discharge during all these subintervals are independent variables, except one is your dependent variable. So that one is your Q1, equation 6. So that equation 3, 6. So how to get Q1? That is dependent variable. Substituting the water continuity equation here, a little bit analysis is there here. So you have to practice it. You have to write it and practice it. So therefore, you should remember those equations. You see here. Now substituting 3 in the equation, this is water continuity, and 6 is your Q1, dependent variable. So that is water discharge dependent variable. Substitute that one, then you take partial derivative with respect to that one. So you are going to get this one. Understood? So this is the equation which you are going to get dou L2 dou Q1 using equation 3 in equation 6. This equation in that 6. Then take partial derivative. So hope again I will go back. So use that equation 3 in this equation. Okay. Then you take partial derivative L2 with respect to Q1 only. Q1 only you have to consider. So when you differentiate that one with respect to Q1, then we are going to get this equation. Just you substitute it. So all the analysis, you are going to get this one. So all simplification if you want to do, so you can do it because each step, some mathematical simplifications are required here. So therefore those mathematical steps, intermediate steps, please you do it. I am telling equation using equation 3 in 6 and taking that one with respect to Q1. So you are going to get this equation. Still, if you are not getting after doing the intermediate steps, you can ask me in the next class. No problem. At least you have to try because everything, if I'm doing it, it's intermediate steps. So then it is, you are not going to learn anything. At least intermediate steps. So you do it. So I'm giving the hint here. So substitute, use equation 3 in 6, take partial derivative with respect to Q1, that is dependent variable. Then you are going to get this equation. Call this as equation 11. Okay. Let me clear this one. Dual variables lambda 1m, lambda 2m, lambda 3m for any subinterval may be obtained as follows. So dual variables are your lambda 1, lambda 2, lambda m. So how to obtain lambda 1m? So from equation 7. Similarly, lambda 2 from equation 8. Lambda obtain lambda 2 1 from equation 10 and other values from lambda 2. So lambda 1m, lambda 2m, 7, 8. I will show you equation 7, 8. So this is your 8 you are going to get from equation 8. Lambda 1m you are going to get after solving this one. Equation 7. This is your equation 7 we are having it. Some equation deviation is there here. 8, 9. The one from 8. Sorry. Equations I have to change, so I will change it now only. Eight, 9. Okay. Yeah, now I changed. So equation 8, 9, you have to get it. Now you see equation 8. This is your 8. From this one you are going to get a lambda 1m. From 9 lambda 3m you are going to get. Okay. So this is your 10 equation. Okay. Now you can see, go back and see 8, 9. Then lambda 2 1m from equation 10 we are getting it, and other values of lambda 2 of m, because lambda 2m is from equation 10. Okay, wait, I will check the equations. I think the equations are mismatching. Lambda 2, equation 10. Yes, this is 11, this is 10. Now it is okay. Yeah, lambda 1 from 8, lambda 3 from 9, lambda 2 1 from equation 11. Equation 11, that means which is your equation 11? This is your equation 11. From this one you are going to get lambda 1 m. Then coming back to this equation. So remaining values where m is not equal to 1, that means 1 will be independent variable. Other independent variables will be calculated from your equation 10. So this is how the dual variables for lambda 1, lambda 2, lambda 3 are obtained. Then the gradient vector is given by the partial derivative of the Lagrangian with respect to the independent variables, the gradient vector. So how it is given with respect to the independent variables? Q1 is your dependent variable. So other than 1, if you are taking it, Q of m, where m is not equal to 1, because one variable will be dependent variable. So if you are taking this equation, you are going to get it from that Q equation only. If you are taking that one, so you are going to get this equation. Same thing which I have shown it in the previous slide. That we have taken it with respect to Q1 alone. We have taken Q1 alone. I'll go back and show you. See, Q1 alone we have taken it. This is the equation. But when you are taking Q to the power of other variables M, where M is not equal to 1, because for M is equal to 1, already we got different equation here. So for other variables of discharge, that is where M is not equal to 1, so independent variables, you are going to get this equation. So just intermediate steps are missing, just to take the partial derivatives of this one. So only thing is, remember that one, in the water discharge rate, during each subinterval, all the variables, that is discharge rate is considered as independent variables, except one variable as dependent variable, that is Q1 is your dependent variable, other than Q1, which is your independent variables. So that's why we are getting it for Q, two equations. One is with respect to Q1 alone, the other one is with respect to Qm, where M is not equal to 1. This is the thing you should remember it. Now optimality, for optimality, the gradient vector should be 0 if there are no inequality constraints on the control variables. That means for optimality, so this gradient vector must be equated to 0 if there are no inequality constraints. Understood? So that is the thing we have to consider it. Sometimes, so this is the hydrothermal solution, how we are going to get. So they may ask just hydrothermal generation, optimal scheduling of hydrothermal generation. So till this point, you have to get it. So optimization problem as well as your solution. So optimization model, solution. We have got so many equations, isn't it? So any model will have its own algorithm. Any model you are developing, so it will have its own algorithm to obtain its solution. So what is that algorithm? So algorithm may be represented in terms of steps or in terms of a flow chart. This is how it will be represented. So now let us see what is the algorithm. So assume, we'll solve one numerical, we'll see that one, you will understand in better way. Assume an initial set of independent variables. Please remember, independent variables for rate of discharge, water discharge Q is Qm, if you are representing, in which one variable will be dependent variable. So therefore M is not equal to 1 for all subintervals except the first. That is the meaning. This is the algorithm. So assume initial set of independent variables. Understood? Assume the initial set of independent variables Q1, Q2, Q3, Q4, Q5, Q6, Q7. Q1 we are not going to assume it. Why? Because Q1 is your dependent variables. So that is the first part. Obtain the values of dependent variables. As I said earlier, dependent variables are your PGT, PGH, real power generation due to thermal, real power generation due to hydro, water continuity, that is water storage, X during each, M means during each subinterval. And in addition to, what is the other dependent variable? Your rate of water discharge. One variable will be, that's why I represented 1. Here it is independent variables. Here these are your dependent variables from equations 3, 4, 2 and 6 respectively. So this Xm from equation 3, PGH from equation 4, PGT from equation 2, Q1 from equation 6. You have to solve it. So obtain these values. First step is initial all the independent variables except one variable which is treated as dependent variable. Then our second step, obtain the values of all dependent variables using the equations, respective equations. Clear? So you should know that one. Then obtain the value of your dual variables, lambda 1, lambda 2, lambda 3, m during each subinterval. And these lambda values, you should not calculate it for your dependent variable. So that dependent variable will be m is not equal to 1. Understood? So that way you find out the obtain the values of this one using equations 8, 9, 10, 11. 8, 9, 10 is for lambda 1, lambda 3, lambda 2 respectively. Then lambda 2, 1. See here, lambda 1, lambda 3, lambda 2, but we want mth, m is equal to 1. When m is equal to 1, that is becomes your dependent variable. So during that one, which equation you have to use? Equation 11, you have to use it. Clear? So these are the equations, you have to use it. Step 1, independent variables, assume it. Step 2, find out the values of dependent variables. Step 3, obtain the values of your lambda, that is dual variables. Then step 4, obtain the gradient vector using equation 12. Last one we have seen. And check if all its elements are equal to 0 or within the specified accuracy. If so, optimum is reached. Otherwise, go to step 5. That means this equation 12, check the gradient. Equation 12, this one. You check this one. Some tolerance value will be specified. You check whether it lies within the some tolerance value or within the specified limits. If it is yes, then you have reached the optimality. So stop it at this point only. So that will be your optimal. So whatever the values you have calculated for these dependent variables and dual variables will be your final solution. Otherwise, if it is not lying within the specified limits, then what you have to do? You have to go to step 5. That means you are not reached the optimal condition. So therefore, you go to the next step, that is 5. Now what you have to do? Obtain new values of control variables using the first order gradient method. Understood? So what is your control variables here? That is the equation. Can anyone tell what are the control variables? See here. In this equation, okay, see. What is control variable? I told several times, isn't it? It is your rate of water discharge. So I didn't get answer. That is your control variable. So what is your control variable? Water discharge. Understood? That is Q. Dependent variables. Dependent variables. Real power generation due to thermal. Real power generation due to hydro. Then your storage X. In addition to these three, there is one variable which is dependent, that is known as Q1. Q1. Clear? So then independent variables, you are having it anyway, that you are having it. We have seen it. Okay. So go to this one. So find out the new value. So that is Q new M is equal to, that is rate of discharge is equal to Q volt minus alpha of dou L to dou QM, where M is not equal to M. That means when you substitute M is equal to 1, it becomes dependent, isn't it? So we have to find out the new values of control variables. So Q new M is equal to Q volt minus alpha of your gradient, whatever the gradient we have obtained from equation 12. So that gradient, and alpha is your, what is this one? It is a positive scalar. You can select it. So this value you have to select it appropriately, or sometimes this alpha value will be given it. This alpha we have already discussed in convergence criteria when we have studied about your thermal stations. The same procedure here also you can apply in order to select the alpha value. So which must be a positive scalar. Then repeat from step 2. Understood? Find out the new value of independent variable. Repeat from this one. Again, find out dependent, dual variables. Again, find out the gradient to 12. Check whether it is within the limits or not. If it is not right, stop it. Otherwise, again go to 5. Next, again you find out the new value with the positive scalar alpha value. Again, come back to. So this process keeps on repeating it. This is the algorithm steps. Sometimes they may ask, explain the algorithm. Explain the algorithm for hydrothermal scheduling. Hydrothermal optimal scheduling. Algorithm for hydrothermal optimal scheduling. So these are the steps you have to write and you have to explain it. So you see the marks, then you answer it. If they ask only write the algorithm or explain of the algorithm. If it is 5 6 marks are there, just you write these steps and you mention how alpha is selected. If it is 10 marks, then each step you have to explain it. What each step you are doing it, second step what you are doing, third step what you are doing it. Like that you should explain whatever the explanation now I have given it. So those explanations you have to give it. So now here in this hydrothermal, the concept is simple. You got additional constraints because of water storage, rate of discharge, inflow variable J, isn't it? So some different variables you are getting it. So you are getting additional constraints here. So those constraints, those equations, just you practice it, and so it will become easy for you people. So this is the thing. So next class we will try to solve one numerical problem. I will check whether it has been asked, if it has been asked in the question papers, previous question papers, or if it is available in your assignment, then I will take up the numerical problem based on your hydrothermal power generation, that is optimal scheduling. So please all of you go through these steps, that is from the discretization onwards. What is the water continuity equation, what is power balance equation, what is the power generated by hydropower plant, how those has to be, these three equations, constant equations, to be augmented in an objective function along with the cost function. Then what are the Kuntakar condition, taking partial derivatives and equating to 0 with, you have to take partial derivatives with respect to the dependent variables, that is Pgt, Pgh, X. In addition to these three, we have additional dependent variable, that is water discharge rate, that is only one water discharge rate, that is Q1. So with respect to these variables, four variables, you have to take partial derivative from the Lagrangian equation. So you will get the resultant equations. From those resultant equations, you are going to find out the dependent variable values and the dual variable values. After getting that one, each time check the gradient. If gradient is within the limits, then it is optimal. If it is not new, then you find out the new set of values. Q new we have to find out during each subinterval. Then again repeat step 2 to 5, etc. This cycle goes on till you get optimal solution. Hope you understood this one. So any doubts till this point? If you have any doubts, oh, you can put it in a chat box or you can unmute yourself and you can ask. Anyway, Friday onwards, if people are coming, and end the class.